Okay, guys, so let's go over this question. Let's go over 6.1. If you're finishing on your own, feel free to do that. I've set it up for you already, and so let's figure out, like Josh said, would you rather get hit by a car moving at 65 miles per hour or a truck moving at 30 miles per hour? Okay, so let's calculate that out. So we got 1/2, which is 0.5 times 1,000. Times 29.058. But since it's squared, we need to multiply it twice, or you can just square it on your calculator. And that's the amount of force that you'll be getting, that the car will be moving with. Okay, so 422,183.682, and it's going to be in joules. Okay. Okay, so 422,183.682 joules. Okay, now let's try it with the truck. So we got 0.5 times 10,000, 1, 2, 3, and then we're going to multiply by 13.411, 13.411, and so we're going to get 899,274.605 joules. Okay, so which one would you rather get hit by?
The truck.
No, definitely not the truck. You want to get hit by the car. Okay, but I want you guys to notice something. The truck it's 10 times heavier than the car, right?
Yeah.
Right? It's 10 times heavier. But if you take a look at the amount of force that they're moving with, it's only about it only has about twice as much force, right? And the reason why is because if you look at the velocity, it's squared, right? So the speed has a much bigger impact on the energy than the mass does. So obviously, the bigger the mass, the more force you have, but the faster it's moving, it's going to have an exponential amount impact on the amount of energy produced, okay? So that's how you use that formula. Just need to know how it works, yeah.
So how hard or how much energy is that? Like
a lot.
Okay.
Just think about it, a car, and this is a small car, 1,000 kilo. Actually, that's a pretty normal car. Getting hit by a car 65 miles an hour. So go to the freeway right now and then just see how fast they're moving. That's the energy that they have, okay? All right. Any questions? Okay, so that's kinetic energy. There's different types of energy. We'll be talking about different types before narrowing it down to the one we'll be focusing on. But kinetic energy is based on kinetics, how it's moving. Okay, it's based on motion. Okay, there is also potential energy, okay? And potential energy is the energy in an object by virtue of its position. So it's like stored energy, is how much energy something potentially has. So for example, if you're holding a weight above your head, that thing has potential energy, right? Because if you drop it, what happens? It's gonna come down. Okay, or in a spring, when you push a spring together, there's energy stored in there, which allows it to shoot out. The one that we'll be talking about more will be energy in a chemical bond. So when you have molecules where atoms are bonded to each other, there's energy. If you break those bonds, energy will be released. And so you can kind of think of it this way. Potential energy can be converted into kinetic energy. So if you're at the top of a hill with a bike, you have a lot of potential energy. But if you're not moving, you have no kinetic energy. But as you go down the hill, you increase in kinetic energy because your speed will go up, but you will lose potential energy because you're losing the amount of energy that you can produce as you go down the hill, okay? So just know those are the two main types of energy. You got potential and kinetic, and you can switch or you can convert energy between one another, all right? Any questions about that? Yeah, okay. All right, so in chemistry, we're going to be talking a lot about potential energy. And so we talk a lot about electrostatic potential energy. Now, you guys don't need to copy all of this down. I just need you guys to know how to use this formula, okay? So electrostatic potential energy, this energy comes from interactions between charged particles. Now, we talked about how in an atom, inside the nucleus, we have all the protons, right? So what is the charge of a nucleus? Is it positive or negative? Yeah, it's positive. The nucleus is going to be positive, and then the electrons flying around the nucleus are going to be negative, right? So there's a positive charge and there's a negative charge. Now, these are charged particles and they have some type of energy in between them, okay? So that's what Q1 and Q2 are. We're talking about the charge on the interacting object. So if we're looking at this object right here, this electron and this proton, we can say that the proton is Q1 and the electron is Q2. So for Q1, you would say that it's a positive value, and for Q2, you would say it's a negative value. Okay, the D is distance. So the amount of distance in between those objects, and then K is just a constant. Remember, just like the gas constant, it's just always the same. And based on those values, we can figure out the electric potential energy in between those two objects. Okay, so that's how you use that formula. Now, we don't have to just look at a positive and a negative charge. We can also take a look at the potential energy between two negative charges. So you can look at Q1 and Q2. And so this time Q1 would become negative, and then this would be the distance that we would be calculating. Okay, so it doesn't matter if it's a positive charge or a negative charge. We just need to specify which two objects we are looking at. Now, one thing that's very important is this right here. Okay, if the electrostatic potential energy, the value that you get is positive, the two objects are going to push each other away. Okay, which makes sense because if we have a negative value here and a negative value here, right? If we have two negatives, what do they do to each other? They push each other away, right? And so negative and negative will make a positive value, which means it will repel, right? Same thing if it was two positives. Two positives would give you a positive value, which means it would repel, right? Because a positive and positive charge pushes each other away. So we already knew that like charges push each other away, but this formula gives us a way to calculate the values for that. Okay, and then vice versa. If the net value is negative, they will attract, which also makes sense because if we have a positive and negative charge, we know that opposites attract, right? And mathematically, if we solve this out, it will give us a negative value for the electrostatic potential energy. Okay, so this point right here kind of tells us what we already know, but it's kind of nice to know just off the top of your head that if when we use this formula, if the value is positive, they repel. If it's negative, they attract. Okay, the other thing that we want to know is the lower the number, right? The lower this number is, the more stable that interaction is. Okay, which makes sense because if we have a positive and negative charge that's really far away, right, it's very easy to disturb that system, right? Like in a long distance relationship, if you are very far away from your significant other, right, something else, you know, some dude might come and steal your girl away, right? But if you guys are closer together, then that it's harder for that dude to come into the picture. No, never long distance. One and done for me. My wife's my first girlfriend. All right.
Really?
Yes.
Oh, wow.
All right. Anyway, so let's use this equation to demonstrate, like we just said, the interaction, how like charges changes with distance. Okay, so we're going to take a look at this equation. So we have the electrostatic potential energy. The K value is never going to change. Okay, so if Q1 is positive, we can just put positive 1 right here. Okay, because it's a like charge. So like charges means it's either two positives or two negatives. Okay, we're going to throw another positive value in there for Q2. And then so if we take a look at this, if we put in D for distance. And so if we use this equation to solve it out, we'll get positive K over D. Okay. And if you notice, this fraction, this value right here is positive. So if it's positive, will it attract or repel? Yeah, it's going to repel, which makes sense because if we have two positive charges next to each other, they're going to push each other away. Okay, so again, this mathematically just shows us that what we already know, like charges push each other away and opposite charges attract one another. Okay. What's up?
Hi, Professor Edwards' class.
Yeah.
I wonder if we could borrow 2 posters of like the lab safety.
Oh yeah, it's right there on the yellow. You can just take that whole stack.
Oh,
Yeah,
okay.
yeah.
Thank you for
Yeah,
sharing.
of course. Okay, make sense? Okay, because you will have to use this equation on the AP test without getting any numbers. Sometimes they'll just tell you, hey, it's 2 positives or 1 positive, 1 negative. And you'll have to be able to substitute in values like this in order to figure out how it's going to affect the electrostatic potential energy. Okay. All right, 6.3 is the same thing, but it's with opposite charges. So you would do the same thing, but you would plug in -1 for one of them, and you would get a negative value, which means that the objects will attract. Okay. All right, so let's move on. So we're going to talk about units of energy. So this is how we measure energy. It's typically measured in joules. Now, you guys don't need to memorize all this. Some of them are going to be on that equation sheet that you guys have, so don't feel obligated to memorize them. But 1 joule is basically measured as 1 kilogram times meter squared divided by second squared. Now, that might be kind of hard to conceptualize, but it's just there so that we know how to cancel out our units, okay? Okay, 1 joule or 1,000 joules equals 1 kilojoules. We'll see kilojoules a lot when we're doing our stoichiometry with this unit. And then we know calories, right? Now, the calories that we know that we talk about in food is called a kilocalorie, kcal, and it's 1,000 of these small c calories. And 1 small c calorie is 4.184 joules, okay? So later we'll be talking about nutrition facts a little bit to see how much energy is in there and how we can convert that energy in chemical reactions. Okay. So yeah, just know these are different ways that we measure energy. There are a few other ones, but these are the main, I guess, 4 that we use. Okay, we have joules, we have kilojoules, we have little c calorie, and we have big c calorie. Okay. No. So we're not eating energy, we're eating chemicals, and in between the bonds there's energy, and our body uses the energy in those bonds. But yeah, Einstein's theory of relativity equals mc squared. It actually tells us that energy and mass, you can convert between the 2 of them. Yeah. If you know about antimatter, that's where we get that concept, because you could turn that mass directly into energy, 100% efficiency, which is a lot of energy. Okay, so when we talk about energy in chemistry, we need to always specify what we are looking at. Okay, so we have to identify the system and the surroundings. Now, the system is the area that we are observing. Okay, and so in chemical reactions, when we have like a equation, right, a chemical reaction, the system will usually be the chemical reaction, okay? And the surroundings is everything else. So let's think about it this way, okay? So since you guys like my fart analogy so much, let's use fart, okay? So this is Mr. O, and we're gonna draw some fart, okay? And it's gonna be in this small box. This is the classroom, okay? So we always have to make sure that we specify the system and surroundings, because it'll actually change how we describe what we're looking at, okay? So let's take a look at the fart, okay? So let's say right after I fart, okay? Does it have a higher temperature than the air around me, or a lower temperature? Yeah, it has a higher temperature, right? So that means it has more energy, okay? Okay, but the air around me, we know it's gonna have relatively less energy than my fart, okay? So if we say that my fart is the system, okay, as time goes on, does the system gain energy or does it lose energy? Yeah, it's gonna lose energy, okay? Whereas the air around me will gain energy, right? Does that make sense? Okay, but let's say we reverse it, okay? So I'm no longer looking, my fart is no longer the system. Instead, we'll say the air in the classroom is the system. So if I fart, the air in the classroom, will it gain energy or lose energy? Gain. And then the fart will lose. And so depending on which one you're looking at, you can say the system gains energy or the system loses energy. If I say that my fart is the system, that means the system loses energy. But if I say the air around me is the system is gaining energy, right? So it's very important to specify what we're looking at, because if not, we're going to come up with reverse answers, which is not good. Okay. Now, there's 3 different types of systems that we'll be looking at. And you guys don't need to write this down or like memorize like, oh, this is like, we need to know what an open system is. But you got to be aware of the 3 of them. Yeah, great. What's up? Yeah, so if the air is the system, that means it's going to gain energy, right? Because it's absorbing the temperature from my fart. But then if I say my fart is the system, then it's going to lose energy because it's getting colder to match the temperature of the room, right? And so it's going to lose energy. Okay.
So I can see how this is getting.
Yes, because you need to be very specific. It gets more and more specific as we go deeper into Chem.
And just the conversion and like the
Yeah. Mhm.
that-
Yeah, but you guys signed up for this, so tough. Okay, so open system. Okay, an open system is a system where matter and energy can be exchanged with the surroundings. So a good way to think about an open system is if you had like a cooking pot, right? And you were boiling some water. Okay. When you guys are boiling water, you can, some matter, right? Water vapor is going to go out, exchange with the system, and then energy is going to go out as well, right? Right. Okay. That would be an example of an open system. Open system is where matter and energy can move back and forth in between the system which you're looking at. An example of a closed system is a system that can exchange energy but not matter. So I like to kind of think of this as like a glass jar. If you have a glass jar, right? And let's say you pour some hot water inside the glass jar. The water can't leave the glass jar, right? Because it's trapped in there, it's closed. But we know that temperature constantly is going to go down in the glass jar. So energy will be able to leave the system, but the matter will stay inside of that glass jar. So that's an example of a closed system. So again, we have to be very specific about what types of systems we're looking at. And then last but not least, we have an isolated system. And an isolated system is where matter and energy, neither of them can go between the system and the surroundings. So it's actually impossible in real life to have a completely isolated system. But the best way I like to think of it is if you have like a hydro flask, right? If you close the hydro flask, the matter in there can't leave the hydro flask, and the energy leaves it very, very slowly, right? And so eventually it will cool down. So it's not truly an isolated system, but it's kind of a daily thing that we use that best represents an isolated system, right? So I'll write hydro flask. It's where energy and matter both stay inside of the system. Okay. So just know that there are 3 different types of systems. I'm not going to ask you, and the AP test is not going to ask you, hey, define an open system or define an isolated system. But just know that those are the kinds of systems that are that exist in this unit. That would be a great question. I wish that was a question. I will not. I love y'all, but not that much, if at all. Okay, let's move on. So we actually just talked about, so we'll skip 6.3 through 5. Instead, I want to go into this. I think this will be the last thing we cover today. Okay. So energy can be transferred either through work or heat. Okay. So again, a lot of definitions at the beginning of this unit. So I do want you guys after this class to review this information. You guys should be catching up with or staying on top of your reading. But energy, we can transfer energy through work or heat. Okay. Work is energy transferred to an object when it's moved by a force. Okay. So for example, if you lift an object, you are transferring energy to it, right? Because let's think about it. Okay. So we'll do this. Okay. So we got a big dumbbell, and this is Mr. O, okay? Because y'all know I lift. Okay, so Mr. O is gonna lift. Actually, let's add some more weight on it. Yeah, let's add some more weight. Okay, so Mr. O is gonna lift this object, right? So when Mr. O lifts this object, it's gonna increase in potential energy, right? Because if it's on the floor, doesn't have much energy, but when it's high up, right, then it's gonna have more energy. So work, I'm putting in work into the weight, and that's how I'm transferring energy. I'm taking the energy that's inside my body, right, from the food that I eat and the sleep that I get. I'm taking that energy and I'm putting it into the weight by lifting it up. Okay, so that's one way we can transfer energy. Another way we can transfer energy through work is if we bring two like charges together. So I don't know if you guys have ever done this. I did this a lot when I was a kid. When you have a magnet, right, you take the positive and the negative side, or sorry, the positive and the positive side, and then you try to put them together. Have you guys ever tried that? Got two magnets and okay, maybe I might be the only dumb one, but you get two magnets and try to put it together. What happens if you try to get them really close? It gets really hard, right? Like you try really hard, you're like shaking and try to put it, and sometimes it'll just like spin off. And so that's another way we can transfer energy in between two objects. We can bring two like charges together. If you guys have never tried that, get two magnets and try to put them together. It's like impossible. Okay, so that's how you transfer energy through work. In chemistry, though, we're not going to be talking too much about that. We'll be talking more about heat, which is why this unit is called thermochemistry, because thermo heat. And heat is energy transferred from a hotter object to a colder one. Okay, and so energy transferred between a system and a surrounding is a result of its difference in temperature. Okay, so in chemistry, we don't believe in hot and cold things. We just believe in things that have more energy and less energy. Okay, and so energy always flows from a hotter object to a colder one. Okay, so remember that example with my fart, right? Okay, my fart has more energy, and so my fart is going to transfer energy to the air around it. Okay, it's not going to cool, the air around me is not going to give cold energy to my fart. Instead, the energy is going to go from high to low. Okay, that's always how we want to think about it. Okay, and then for temperature, just know it's a measure of how much the particles are moving. If it's a higher temperature, the particles are moving faster, which is more energy, and lower temperature is slower moving and it's less energy. Okay, so I know that was a lot of definitions at one time, but this is kind of the introductory information that we need to know for this unit. Any questions about any of this? Okay. Energy is all about transferring things. Heat is moving from higher energy to a lower point of energy. Okay, first law of thermodynamics, energy is always conserved. You can't create or destroy new energy. Energy only moves from one place to another, okay? So it goes from high energy to low energy. They want to reach something called thermal equilibrium, which is where they all have the same energy, which is why if you have something warm, it ends up becoming cooler to match the temperature around it. Vice versa, if you have something cold, it's gonna get a bit warmer to match the temperature around it, okay? And so we have something called internal energy, and make sure you guys are very careful with the units now. It's capital E, and it's the sum of all the energy in a system, okay? And so it's like everything in a system. So if we look in this classroom, it's gonna include the energy inside your body, the temperature of the room, the movement of the molecules, the energy from the light that's around us, the energy of the electricity moving in the wire. So internal energy is a lot of different values, and so we can't really calculate the exact value of internal energy. So in this unit, we're going to be looking at the change in energy. Okay, so this triangle, it's the Greek alphabet, it's delta, but it always means change. Okay, so if you see delta in front of anything, it just means change. So if it's delta E, it's the change in energy. If it's the delta T, it's the change in temperature. Okay, so on and so forth. Okay, and the way that we calculate the change of anything is the final minus the initial. Okay. Okay, so if I wanted to find the change in energy, it would be the final energy minus the initial energy. Change in temperature would be the final temperature minus the initial temperature. All right, so even more definitions for you guys. We're getting close to the actual problems. Okay, but energy of a system, it can change through heat or work. Like we said, we can move energy around through heat or work. And we use Q to represent heat. Okay, so if it's a positive value, the energy in the system was increased. And if it's negative, the energy in the system was lost. Okay, same thing with W work. All right, so I know that was a lot of stuff, so I'm gonna give you a chance to try out what you learned. I want you guys to try 6.7. I'll give you a minute to try that with the person next to you. Let's just pretend that we have a piece of metal and we're heating it with a blowtorch. Did its internal energy increase or decrease? Actually, let me rephrase. Did the internal energy of the metal? Okay, take a minute to try that. You're going to have to use that equation up here to explain your answer. Okay, I'm sure we all know what the answer is, but try to use the equation to prove it. It decreased. Alrighty, guys. So this is very easy, right? If we just think about, did the energy of the metal increase or decrease? Yeah, obviously it increased. If we get a blowtorch on it, it'll increase energy. But let's use this equation to prove it. Okay, so we have delta E equals Q plus W. Okay, so we're saying that the delta E increase, which means it has to be a positive value, right? Okay, it has to be a positive value, which means that one of these is going to have to be a positive value. So let's look at Q. Q is heat. Would the Q be a positive value or a negative value? Yeah, positive value because the system gains heat, right? We're increasing the temperature of the particles of the metal. What about work? Are we doing work on the system? Is it a positive or negative value? Are you sure? Okay, so if we have a piece of metal and we hit it with a blowtorch, let's assume it doesn't move. Okay. Are we doing any work to the system? No, right, we're not moving it any distance, right? Because if you look at the formula for work, it had to have some distance on it. So this value for work actually is going to be 0. There's no work done on the system. Instead, the only thing we're doing is we're increasing the heat of it, which is why the energy increased. And that's how you would prove it using this equation. Okay. So again, I know that a lot of times we use numbers to back up our claims and things like that, but there are times you're going to have to just use the equation to explain conceptually why the energy goes up. We're not doing any work to the system unless, like, you know, we start moving the system, like while we're heating it, we lift it up or something like that. That would be work, but we're not doing any work to the system. Yes. Yeah, you would increase it the moment you strike it. Yeah. What's up? Yeah. I guess so, yeah. Okay, we'll do one last problem and we'll be all done for the day. Okay, 6.8. And we'll pick up at 6.9 next time. Okay, so we have a chemical reaction down here. Hydrogen gas and oxygen gas produce water, liquid water. We're saying that the chemical reaction releases energy. Okay, I want you guys to tell me, do the reactants or the products have greater internal energy if it releases energy? Okay, and I know this is not balanced, but if it makes you guys happy, I'll balance it. Okay, so I want you guys to use that equation again, the internal energy equation. Prove that this which side has greater internal energy. And again, it releases energy. Maybe 30 more seconds to finish that up. Alrighty, guys. So if you're finishing up writing your explanations, feel free to finish up, but I'm gonna go over on the screen so that we can finish this last problem. Okay, so if it releases energy, obviously we know what the delta E is gonna be. Is it gonna be positive or negative? If it releases energy. Okay, so let's think about it, okay? So let's think about a cup of coffee, okay? So if we have a cup of coffee, right? And it's releasing energy into the surroundings. Is there going to be more energy inside or less energy? Less. There's going to be less energy. So that means the change in energy was negative. Okay, the delta E is going to be negative. So remember, if it releases energy, the delta E is always going to be negative, right? Because you're losing energy, right? You're putting out energy into the surroundings. Okay, if you're absorbing energy, it will be positive. Okay, so the delta E is going to be negative. Okay, so if the delta E is negative, that means we lost energy. Okay, so was there more energy in the reactants or was there more energy in the products? Yeah, the reactants will have more energy, right? Because in order to lose energy, you need to have more energy in the reactants than the products, okay? Which means the Q would have to be negative because we lost heat. Okay, now, we can also conceptually figure this out too. If you guys take a look at the reactants, what state of matter are they? Yeah. They're both gases, right? And if you look at the product, what's the state of matter? Liquid. Now, if you guys think about it, which one has more energy, gases or liquids? Gases have more energy, right? Because if you just think about it, if you boil water, it turns into water vapor. Gases move around more than liquids do. So gases inherently have more energy than their liquid counterparts, right? And so that shows us, just conceptually based on what we know, that this system, this reaction has to lose energy because we're going from two gases and we're turning it into a liquid. Okay, which means that we lose, the heat is negative. We're losing energy, we're losing heat, okay? Because we all know when we go from gas to liquid, when we go through condensation, it's getting colder. So we're losing energy through that process, okay? Make sense? So a lot of conceptual stuff. I know we haven't done any number math yet, and I promise you we will, because I know you guys like doing that a lot. But just know that you need to know how to use these equations to conceptually explain these processes too. Okay, you guys already know a lot of things that'll help you explain it, like the gas liquid thing. It's a good way to explain it, but you guys just need to get creative in the way that you think about it, okay? All right, that's gonna be it for today. I'll give you guys a few minutes, just kind of hang out and just relax. This will be posted on Canvas if you need it, but yeah, thanks for today, guys.